This is part one of logarithms. We've already talked about exponentials, and I want to emphasize to you the definition of a logarithm. A logarithm is written in such that the log base b of a, well, let's talk about the b. The b has to be a positive number. It can't be a negative number, and it cannot be 0. And one more thing, it cannot be a 1. A has to be greater than 0. And so if we have a log base 10 of -4, we would say that that does not have a real solution. Our calculator would indicate that by saying domain error, or on some scientifics just says error. Here's an unusual one, the natural log of -1. Some graphing calculators will allow you to go into the complex form a plus bi, and you'll find that this solution is actually pi I, which is the complex solution 0 plus pi I. Now, a scientific calculator will just say error, but I want you to know there is an imaginary solution to these negative logarithms, but our typical response is no real number. Okay, next thing I want to talk to you about is how an exponential is the inverse of a logarithm, just like adding is the inverse of subtracting and vice versa, just like multiplying is the inverse of dividing, just like squaring is the inverse of square rooting. Logarithms are the inverse of exponential. Now, inverse will follow more later as we discuss this, but b, the base, and the y are switched when you do the inverse. So I'm switching x and y here. You'll notice that. And then when I place it in exponential form, I get b to the x equals y. So the actual logarithm will look like the inverse of the exponential. And again, we run through the definition of a logarithm where b has to be positive and a has to be positive also. 0, log of 0, again, is not a real number. So now let's move to why are we doing logarithms? And a good example of that is to just do an example. Here's 10 to the x equals 129. Well, we know that we don't know what 10 to the x is, but we do know that 10 to the second is 100, and 10 to the third is 1,000, and that 129 is somewhere between 100 and 1,000, and obviously it's a lot closer to 100 than it is to 1,000. So when we do this on our calculator, we say log base 10 of 129. Of course, our calculator does base 10. Turns out to be approximately 2.1. And again, equal sign turns into an approximation because I'm rounding this off. So logarithms exist because the exponents are not always whole numbers, or even they could be decimals, and that's why we use logarithms. Next thing I want to remind you of is that exponentials are logarithms, and especially I want you to see here that the way we write exponents is base to the exponent equals this value. And when we rewrite that as a logarithm, the same terms are used, base, but that's a subscript. And then the antilog, well, that's this value right here, equals the exponent. Now notice the exponent where it was in exponential form. So to kind of illustrate that here, I have a little story. I have 10 to the second power equals 100. That's a true statement. And a log comes along and pounds 10 on the head. Well, 2 runs over to tell 100, and 100 comes to see what's going on. So this is kind of an illustration of how to change an exponential into a logarithm. So log base 10 of 100 is 2. And again, here's another illustration of that. 2 to the 5th equals 32. That's a true statement. To change it into logarithms would be log base 2 of 32 is 5. Again, here's our basic definition. Here's some of the log rules that we want to emphasize. And this one is called the equality rule. And the next one is called the base change rule. Log base x divided by log b. Now we're in base 10. This is the one rule where you can do it either as log base 10, which is called common log, or the natural log, ln. That's an ln, not an in, of x over the natural log of b. This is when you use your calculator. Here's a form that you will use also. Log, here's a base b with an exponent that is the log base b of a. Notice how those two bases there match, and the solution is a. This is the product rule, which means u times v expands. This is an expansion where you would rewrite this as log base b of u, log base b of v. The division rule, similar to the logarithm rule, except it's a subtraction. So I have log base b of this fraction, u over v. I expand that, or write it, as two separate logs, logs base b of u minus log base b of v. And the last one is the power rule, and that's log base b of u to the n. The power here, n, goes out to the front as a multiplication. So I have n times log base b of u. A lot of times people confuse this with other log rules, and we'll compare those in a little bit. So again, here's my definition. To re-emphasize it, here's a definition of logarithms and the limitations on that. This is called the antilog equality theorem. That's right here. The next one is called base change. Again, a base equality rule. The base matches the base of the exponent base. The product rule, we learn this under exponential rules as b to the u times b to the v. Well, what do you do when you multiply like bases? Well, you add the exponents. And then we have the quotient rule in exponentials, which says b to the exponent u divided by b to the v. Well, what do you do with the exponents? You subtract them. That's an error right there. That should be a minus. And over here it's a minus also, if you correct that. And the last one is the power rule. You're used to this one. B to the u to the n power means you multiply u times n. Again, that's a correction. That should be an n right there. So over here, the power rule for logarithms follows a similar pattern. The n goes to the front. Take it off of this exponent here. So I want to emphasize again the logarithm properties, and to illustrate them, changing, you'll notice this logarithm to an exponent. The simplest logarithm rule is log base b of 1 equals 0. If I convert this to an exponential, it would look like this, b to the 0 equals 1. Notice the color coding there. Example of that would be log base 4 of 1. Well, the answer would be 0. Check it. as an exponential, 4 to the 0 equals 1. Log base b of b equals 1. Here it is written as an exponential. Illustration of that would be log base 3 of 3 equals 1. Here's the same thing written as an exponential. You could understand 3 to the 1 is 3. Here's log base b of b to the a is a. Example of that would be log base 5 of 625. Now remember, 625 is 5 to the 4th power. 5 to the 4th power means this 4 up here would be the solution. Here's the same problem written as an exponential. Here's my 5 to the 4th, which is really 625. Same base rule again. Base change formula. Let's see this illustrated. Log base 2 of 15 on a calculator you would put in as log base 15 over log 2. Give you the same answer as the natural log of 15 over the natural log of e. Now you can't just use log and natural log interchangeably, but on base change formula, either one works, and that's because they're both in base 10 or they're both in base e. Another example of that would be log base 4 of 29. I would want you to look these up on your calculator. So log 29 over log 4, or log 29, natural log 29 over natural log 4. So one example of these would be log base 7 of 49. Well, that would be log base 7 of 7 to the 2nd, which equals 2. So 2 would be the solution of that. And I am in this problem referring to the power rule right here. Or actually, sorry, I'm referring to the equality rule here. Another example would be log base 7 of 1/7. Well, 1/7 is really 7 to the negative 1. So since these two bases match here, that means this would equal negative 1. Log base 6 of x equals log base 6 of 5. Well, that is referring to the equality rule right here. There's your equality rule. And so that would mean that x equals 5. Another example using these would be log base 2 of 128. Well, 128 is actually 2 to the 7th. If log base 2 of 2 to the 7th, then the 7 comes out front. Now this is not this power rule here. This is instead a rule which emphasizes the matching of these two bases. Okay, and the last of these would be log of 0.01, which is 1 over 10 squared, which equals the log of 10 to the negative 2nd. Remember your negative exponent rule, and the solution is negative 2. Then log base 4 of negative 1. When you put that on your calculator, you would realize that that violates this rule. U has to be greater than 0, so that would be no real solution, even though it has an imaginary solution. And the last example would be log base 11 of 121. Well, 121 is 11 squared, and base 11 of 11 squared is 2. So this concludes the part 1 of logarithms on the definition and rules of logarithms. I know this is long, but we've probably covered 12 different examples of this, and hopefully you've seen the logarithm rules illustrated, and we'll continue to do that in part 2 and part 3. So look for that to follow. Thank you.